A new paper called Optimizing RAG Rerankers with LLM feedback via reinforcement learning makes a pretty strong claim. Reranking isn't just a sorting problem. It can be framed as a sequential decision-making problem. More specifically, the paper models reranking as a Markov decision process, where the model selects documents one at a time in order to maximize downstream answer quality. So let's quickly set the stage. RAG, or Retrieval Augmented Generation, is the architecture behind a lot of AI systems that need outside knowledge. First, the system retrieves a pool of candidate documents from a knowledge base. Then, a reranker decides which of those documents should be prioritized. After that, the selected context gets passed to a language model which generates the final answer. So, reranking sits right in the middle of the pipeline. It's the stage that decides what evidence the LLM actually gets to work with. And that's why this framing matters. If you think reranking is just relevance sorting, you'll train it to find documents that look related to the query. But if you think of it as sequential decision-making for generation, the goal changes. The reranker is no longer just ordering documents by topical similarity. It's selecting the context that's most likely to help the downstream model produce a higher quality answer. In reinforcement learning terms, a Markov decision process is a setup where an agent makes a sequence of choices, and each choice changes what options are still available next. That's exactly the structure this paper applies to reranking. At each step, the model picks one document from the remaining candidates, and those choices gradually build the final context shown to the LLM. And that's what makes the paper interesting. In a real RAG system, the LLM can only reason over the documents it's given, so the reranker doesn't determine the final answer by itself, but it does constrain the evidence the model can use. That makes reranking much more than a cosmetic ranking layer. It's an upstream control point that shapes what kinds of answers are even possible downstream. The paper argues that current rerankers are usually trained the wrong way. Most of them learn from static human relevance labels. A human looks at a query and the document, judges whether the document seems relevant, and then the reranker is optimized to reproduce those judgments. The problem is that relevance is not the same thing as generation utility. A document can look relevant and still be bad context for answer generation. Imagine the query is, what causes global warming? A document called Overview of Climate Change might look highly relevant to a human annotator, but if it's just a broad summary with no concrete causal explanation, it may not help the LLM produce a strong answer. Well, a more specific document about greenhouse gases and radiative forcing might look less generally relevant on the surface, but be far more useful for generation. That's the misalignment at the center of the paper. The key idea is to treat reranking as a sequential decision-making problem, specifically as a Markov decision process. In that formulation, the reranker doesn't simply assign one final relevance score to every document. It learns a policy that selects documents one step at a time from the remaining candidate set, with the goal of maximizing downstream answer quality. In practice, that changes the training objective completely. RRPO doesn't train the reranker only to reproduce human relevance labels. Instead, it optimizes the reranker based on what happens at the end of the full RAG pipeline. The reranker selects documents, those documents are passed to the reader LLM, and the generated answer is scored based on its quality. That downstream outcome becomes the signal used to improve the reranker's policy. This creates a very different learning dynamic. The reranker is no longer rewarded for picking documents that merely look relevant to a human annotator. It's rewarded for selecting documents that actually help the reader model produce a better answer. In other words, the model is trained on generation utility, not just topical similarity. The paper also introduces an important stabilization mechanism, a reference-anchored deterministic baseline. In PPO-style reinforcement learning, training can become unstable if the optimization depends too heavily on noisy final outcomes alone. RRPO addresses that by anchoring learning to a fixed reference policy, which provides a stable comparison point during optimization. That makes policy updates more reliable without changing the core objective. The result is a reranker that's optimized for the task it really serves. It doesn't determine the LLM's final answer by itself, but it does shape the evidence the LLM receives. And because the reader model can only reason over the context it's given, that upstream document selection strongly constrains what kinds of answers become possible downstream. So, does this actually work? According to the paper's experiments, yes. RRPO outperforms rank Zephyr, a strong list-wise reranker that already uses LLM feedback on knowledge-intensive benchmarks, and that matters because it suggests rerankers do better when they're optimized for downstream answer quality, not just for relevance in isolation. But the more interesting result isn't just that RRPO works, it's that the learned policy appears to transfer across different reader models. The paper shows that RRPO generalizes to different LLM readers, including GPT-4o, without retraining the reranker from scratch. That suggests the model is learning something more general about document utility, rather than just overfitting to the quirks of one specific reader. The paper also reports robustness to noisy supervision. In other words, the method still holds up even when the feedback signal is imperfect. That's important, because in real systems, supervision is rarely clean. If RRPO remains effective under noisy feedback, that makes the approach much more practical and suggests the learned policy is capturing patterns that generalize beyond the training setup. There's also a practical result here. RRPO integrates cleanly with other RAG components, including methods like query to doc query expansion. Those methods solve different parts of the pipeline. Query to doc helps retrieve better candidates, while RRPO helps choose which of those candidates are most useful for answer generation. Because of that, they can be combined rather than treated as competing approaches. Taken together, these results support the broader point. Expensive human relevance annotations aren't the only way to train rerankers, and for this task, they may not even be the best way. By using LLM-derived feedback tied to downstream answer quality, RRPO shows that reranking can be trained more directly for the objectives that actually matters, helping the reader model produce better answers. And that points to something bigger about how complex AI pipelines work. When you optimize the reranker's policy to decide which documents reach the LLM, you are shaping the context the downstream model is allowed to use. The LLM still generates the final answer using its own learned behavior, but it can only reason over the evidence it receives. That means reranking isn't just a filtering step. It's a control point that constrains the information space available for generation. That has implications beyond benchmark gains. If reranking is handled by a learned policy that shapes the evidence path downstream, then understanding and controlling that policy becomes important for making RAG systems behave the way we want. The reranker isn't deciding the final answer on its own, but it is influencing what kinds of answers the system can produce by deciding what information is available in the first place. From a practical perspective, RRPO also makes a broader engineering point. Upstream stages in the pipeline should be optimized for their actual downstream effect, not just for local metrics that seem reasonable in isolation. Imagine you're building a customer support assistant. You could optimize retrieval for documents that match the user's exact keywords. But what really matters is whether the selected documents help the model produce a useful, accurate response. RRPO shows how reranking can be trained directly for the downstream objective. And the broader lesson isn't that reinforcement learning solves every pipeline problem. It's that sequential decision-making can be a better fit when one stage of a system directly shapes the conditions for the next stage. In setups like RAG, optimizing each component separately with local objectives can create exactly the kind of mismatch this paper highlights. RRPO makes that decision structure explicit and trains the reranker against the outcomes.